Hey there, friends. Today we're going to talk about the third lesson in Module C, which is solving polynomial equations. In the last lesson, we looked at how to factor larger polynomial equations, and today we're going to talk about how do you solve them. So to kind of motivate us through this lesson, we have an ACT question here that we will be able to answer by the end of the lesson, learning how to solve polynomial equations. So this is a straight up ACT question, and that we will answer at the end of the lesson. So the first thing we need to talk about is, in order to solve a polynomial equation, what are you going to do? Okay, the same thing that we did with quadratics, that's what you're going to do. You're going to get the equation, set equal to 0, and then you're going to factor. So when we factor, we always want to look for that greatest common factor first, and then from there we can factor, or we could do anything that we did with a quadratic and then we solve it by the zero product property. So in this first example here, it says, what are the real or imaginary solutions for each polynomial equation? So we have 2x cubed minus 5x squared equals 3x. So the first thing I'm going to do is bring that 3x over, and I set the equation equal to 0. From here, we can see that they all have at least one x in common, and I'm going to use that as my GCF, and I'm going to factor that out, and that leaves me with 2x squared minus 5x minus 3, and then that is still set equal to 0. So from here, you can notice that I have a quadratic here, and we spent a whole module dealing with quadratics, so we can go ahead and say that x out front is equal to 0, and then the 2x squared minus 5x minus 3 is equal to 0. Well, with x equals 0, I already have one of my solutions, but remember the fundamental theorem of algebra says your highest power tells you how many solutions you are going to have. Well, there's one of them. The other two are hidden in the quadratic. So we're going to factor that quadratic using the AC method. So 2 times negative 3 gives me negative 6. What multiplies to give me negative 6 adds to give me negative 5. That would be negative 6 and positive 1. And then we can factor by grouping. Group the first two, group the second two. The first two have a 2x in common. That leaves me with x minus 3. The second set, they don't have anything in common, so I can always take out a positive 1, and that leaves me with x minus 3. So now I can say 2x plus 1 times x minus 3 is equal to 0. And I'm going to split both of those up and set them individually equal to 0, because that's where my other two solutions are. 2x plus 1 equals 0. I'm going to subtract the 1 and then divide by 2. So that solution is negative 1/2. And then the other solution here would be positive 3. We talked about the relationship between a solution and its factor. It's just the opposite. So let's check. Do I have all three? Yes, I do. I have found them all. We're going to do the same thing on part B. We have 3x to the 4th. And it's not equal to 0, so I need to subtract that 6x cubed over, and that would go after the 3x to the 4th, because remember, in standard form, we go from highest power to lowest power. So I have my equation set equal to 0, and now I want to look for that GCF. What do all of these terms have in common? They have a 3x squared, so that leaves me with x squared minus 2x plus 4, right? 3x squared negative 2 plus 4 is equal to 0. Now from here, we can again do our zero product property, and we can set both of these individually equal to 0 and solve. So here, I would say the 3x squared is equal to 0. Divide by 3 and take the square root. That's just going to give you 0. And it specifically would have a multiplicity of 2 because it has that power right there. That's really important. We talked about that in 5.2. Now from here, let's look at this quadratic here. Is there anything that multiplies to give me 4 adds to give me negative 2? Sadly, no. So we're going to have to use the quadratic formula. So we have x is equal to negative b plus or minus square root b squared minus 4 times a times c all over 2 times a. So that gives me x equals 2 plus or minus. Let's remember to simplify that discriminant. And that discriminant would give us negative 12 all over 2. And now from here, you would want to simplify the square root of negative 12. The square root of negative 12 breaks down to 2i radical 3. So I have 2 plus or minus 2i radical 3 all over 2. And you have a Dorito here. So you would say that's 1 plus or minus I radical 3. That was a lot of work, and I didn't have that much room. So if you need to rewind that or pause it or whatever you need to do, please feel free to do so. But from here, let's talk about our fundamental theorem of algebra. It says that we should have 4 solutions because my highest power was 4. And let's look at where those solutions come from. That plus and minus represents 2 different solutions. You have 1 plus I radical 3, and then you also have 1 minus I radical 3. And then remember earlier we said that x equals 0 with that multiplicity of 2, so that counts as 2 solutions. So I actually do end up having all 4. So again, this looks scary, but everything here we have already done. We've done the quadratic formula, we've done factoring, and it all fits nicely here with solving higher order polynomials too. So on this next slide, we would love for you all to pause the video and give this a try. If you're still kind of struggling though, feel free to maybe pause as you work or just go ahead and keep it rolling and we'll stay right here with you. So we're going to go ahead and set this equation equal to 0 and we're going to look for that GCF. Everything here can be divided by 4x cubed. So that leaves me with 3x squared plus 2x minus 12, and then we set that equal to 0. From here, we can do that zero product property and say that 4x cubed is equal to 0. That means x is going to equal 0 with a multiplicity of 3. Because that power right there. Right here with this quadratic, I'm going to have to do the AC method. 3 times negative 12 gives me negative 36. What multiplies to give me negative 36 and adds to give me 2? I don't think anything, so guess what we're going to have to do here, friends? Quadratic formula. So x equals negative b plus or minus square root b squared minus 4 times a times c. And that's all over 2 times a. So I have negative 2 plus or minus that discriminant all over 6. Let me get my mental math brain here working. That's 144 plus 4 gives me 148. And let's see if 148 can break down. Remember the shortcut that we went over, 148 divided by x. And then we go to the table. And let's look in the y column and see if there's any perfect square factor. I don't think there's one that's larger than 4. I think it's 4 and 37. Yep, right there. 4 and 37. Okay, so 148 breaks down into the square root of 4 times the square root of 37. So that would be 2 square roots of 37. So we have negative 2 plus or minus 2 square roots of 37 all over 6. And we have a Dorito. So you notice everything can be divided by 2. So we have -1 plus or minus the square root of 37 all over 3. Now, the fundamental theorem of algebra says that you can have 5 solutions, and let's see where those 5 solutions come from. Remember when we started, we said x equals 0, the multiplicity of 3, and then again we have that plus or minus. Those are 2 separate solutions, so we do have a total of 5. On part B, same thing, but we have some combining like terms to do here and some rearranging of some terms. So we have x to the 5th minus 5x to the 4th, and then that would be plus 6x cubed is equal to 0. So again, we want to look for that GCF. So we would take out an x cubed. That leaves me with x squared minus 5x, and then plus 6 is equal to 0. By the zero product property, we can say x cubed is equal to 0, and then x squared minus 5x plus 6 equals 0. So here, x would equal 0 with a multiplicity of 3 again, because I took x cubed out. And then this right here, I should be able to factor what multiplies to give me 6, as to give me -5. That'd be -3 and -2. So that ends up giving you x equals 3 and x equals 2. B was a lot easier than A, that's for sure. But again, everything that we have done here, we have done before. So this shouldn't be too terribly bad. All right. On this last one, we're going to talk about the special factoring case. And I want to relate this to something that we've already talked about. So you'll notice here that we jump from x to the 4th minus 3x squared, and then I'm going to go ahead and bring over that constant term. Okay. Now, this looks really similar to if I said x squared minus 3x minus 4 is equal to 0. You would know how to factor that because you would say, oh, that's x minus 4 and x plus 1. No, duh, I know how to factor. How does this relate to this? It's the exact same process, except if you jump from 4 to 2 to constant, that still factors the same as -4 and +1. However, it is now x squared minus 4 and x squared plus 1. So anytime you see that jump happen like that, you know how it's going to factor. You just have to put the squared on it. So now the zero product property says we're going to set them both individually equal to 0, and we're going to solve. So we would say x squared is equal to 4. Take the square root of both sides. X is equal to positive and -2. And then x squared equals -1. I take the square root of both sides. X is equal to positive or negative because you put the radical in there. The square root of -1 is I. Fundamental theorem of algebra says we should have 4 solutions, and due to our plus and minuses, we do. All right, we are going to continue this lesson in the second half of the video.